All right, so this is pretty much a follow-up to the previous talk, but I'm not going to use too much of the notation or the details, so no worries if you're coming fresh to this talk. So the goal here is to basically say where can we apply this machinery that Cynthia showed beyond matroids. Okay? So the general theme of this talk is going to be whenever there are certain properties about correlations in pairwise correlations in your distribution, you're going to be able to use this whole machinery to sample from your distribution efficiently. Okay? So let me start by giving you some examples of this. So actually, prior to our work on matroids, there was this amazing work of Federer and Mihai, which showed that whenever your distribution has negative correlation, you can use random walks similar to what Cynthia described to sample from your distribution. And a famous example of a distribution that has this property is random spanning trees in a graph. Okay? So negative correlation means that when you condition on a particular edge E being inside your spanning tree, the probability of any other edge F goes down. Okay? So Cynthia talked about matroids. Matroids don't necessarily have this property, but they have some form of spectral negative correlation. I'll get to what I mean by this later on. But there are also other results in the sampling counting community where correlations are not necessarily negative or positive, but you still can get sampling or counting algorithms that are efficient. One such case is when you have this thing called decay of correlation. So a famous example of this is the hardcore model. So this is a distribution over independent sets or stable sets of a graph, where you put a weight of lambda to the cardinality of the independent sets. Lambda is a parameter that you can play with. So for small enough lambda, White's basically showed that distant vertices in this model are very, very loosely correlated to each other. So the correlation between vertices that are very far apart is almost zero. They're almost independent. And then use this to derive some sampling algorithms some sampling and counting algorithms for this model. Okay? So the general theme of this talk is to derive a method that unifies all of these results and gives you simple sampling algorithms whenever you have any of these properties, but not just these properties. There are others there are other models where we can still do sampling efficiently. So let me give you one such example. So this is a model that was studied by physicists a long time ago. In particular, the seminal work of Heil and Lib showed that this model doesn't have any phase transitions. So this model is called the monomer dimer system. You should think of it as a weighted distribution on matchings of a graph, where the weight of a matching is a product over the weights of the edges in the matching and the product of vertices not in the matching. So vertices not in the matching are usually called monomers, and the edges in your matching are called dimers. These are like pairwise bonds between vertices. And okay, so there are many different formulations. For example, you can absorb the weights over vertices into the weights over edges. So that might be the formulation that you have seen before. Doesn't really matter. But one thing about correlations in this model is that none of the previous three cases applies. Okay, so first of all, to make things simple for me, I'm just going to look at the projection of this monomer dimer system on the set of monomers. Okay, so I sample a monomer from this monomer dimer system, look at just the set of vertices that are not matched. That's going to be my distribution. This is to avoid complications with random perfect matchings, which are unsolved or an unresolved mystery in computer science yet. Okay, so even if you look at the monomer projection, it's still not going to have any of the correlation types I showed on the previous slides. Okay, so for example, if your graph is just a single edge, the two vertices on the endpoints are going to have a positive correlation with each other. They're either both in or out. And there are also going to be long-range correlations. So if you have, let's say, I don't know, an odd path in your graph with weights over the edges being very large, then your distribution basically is supported on exactly 2 near perfect matchings. And so whether or not this vertex is inside your monomer projection tells you exactly whether or not that the other vertex is, right? So you have both long-range correlations and positive correlations. But still, I'm going to show you a method that handles this case as well. Okay? All right. So the general theme is that all of the examples that I showed you, including the monomer distribution, are going to have spectrally limited correlations. And I'll tell you what this means later on. Okay? And this is equivalent to some generalization of log-concave polynomials that Cynthia talked about. So log-concave polynomials imply spectral correlations are negative. Some generalization of it corresponds to having spectrally limited correlations. And the theme is that whenever you have spectrally limited correlations, you get fast mixing random walks for your distribution. Okay. So let me standardize all of these examples that we have seen. So the standard model that we're going to be working with for the rest of the talk is that you have a distribution on subsets of size k out of a set of n elements. Okay. So matroids naturally satisfy this. So for example, if I'm looking at independent sets of a set of vectors or bases that I can form from a set of vectors, they all have the same size, right? Cynthia talked about this random walk that moves between subsets of size k and subsets of size k minus 1 formed from this distribution. Okay. Now, I think the order of slides is swapped. OK, I'll talk about this first. OK, so this is the random walk that Cynthia showed you. You take your distribution on subsets of size k, put it on the top, and you put subsets of size k minus 1 on the bottom. You form a bipartite graph between these two where edges indicate inclusion. And you just do a random walk on this graph. If your distribution is weighted, the weights of every edge in this bipartite graph is just the weight of the top node. Okay? So what that means is that you start from subset of size k. You drop an element uniformly at random because all of the weights going out of that node have the same weight. So maybe you go to this one, and then you add back one element. Here you have to be careful, and you have to choose the element that you add with probability proportional to the distribution of the resulting set. Okay? That's exactly because the weights going out are weighted like this. Okay? All right, so we have this random walk that works for matroids. The other examples that I showed you are not really distributions on subsets of size k of n elements, but there is a standard way to make them into this canonical form, and then we will have a similar random walk for them. So for example, the hardcore model and monomer distribution are not in this model, but you can make them into you can transform them into subsets of size k of n elements, where n here would be twice the number of vertices, and k would be the number of vertices. Okay. So what are the twice the number of vertices elements that I'm talking about? In your graph, you have basically 2 elements per vertex. One is that vertex colored black. One is that vertex colored orange. So colored orange means that you want this to be inside your hardcore distribution or your monomer distribution, and black means you don't want it to be, right? And if I make one of these 2 choices for each vertex, I get n choices. So the set of my n choices would be exactly a set of size n out of these 2 n elements. Okay? So with this formulation, you can also look at sets of size k minus 1 and so on. Right? So sets of size k minus 1 would correspond to not having decided something for a vertex. Okay? So this would correspond to, I don't know, I fixed whether or not each vertex is in my distribution except for the one white one. Okay? So now you can still apply the same random walk that we applied to matroids to this formulation. And what you get is the Glauber dynamics. Okay? So you start from one of these configurations, one of these complete configurations. You basically choose one of the n vertices uniformly at random. You unmark that vertex, so you make it into a white vertex. And now you have two choices to go back up to a set of size k. You choose one with probability proportional to the probability. Okay, so it's exactly the standard Glover dynamics.
So what are the dimers in this graph on the left?
So I've dropped the dimers. So these are just subsets of vertices. I'm only interested in, so in the hardcore model, there are no dimers. In the monomer dimer system, I'm just looking at the projection onto the monomers. Okay, just for simplicity. All right. Okay, so one caveat with this dynamics is that for monomers, this random walk is useless. Okay, can anybody see why? It's because the parity of the number of monomers is always the same, right? It's always going to be odd or even, depending on whether you have odd or even many vertices in your set, right? So if I start from something and I unmark one vertex, I can only mark it with the same color as before, right? So this random walk is not doing anything, right? But there is a very easy fix to that. Instead of moving between sets of size k and sets of size k minus 1, I can move between sets of size k and k minus 2. So I unmark two vertices, and then I mark them back, right? I still get a random walk. Similar to before, this random walk is going to have a stationary distribution that's exactly my distribution. Okay, that's exactly the mu distribution. Right? Okay, so in fact, you can move between k sets and any other size sets. Right? So if you take this idea to the extreme, you can move between size k sets and size 0 sets. That's a trivial thing to do. You just move to the 0 set, the empty set, and then you sample from your distribution in just one step. Okay, so it mixes in one step, right? But okay, so let's make it a little bit less trivial, right? Let's move between sets of size k and sets of size 1. Okay, so this is not as trivial as this random walk, but you know it's still pretty computationally inefficient, right? When you're at a 1 set, you have to look at all possible ways of adding k minus 1 more elements, and that's just too much for us to handle. But nevertheless, bear with me. So okay, so we have this random walk between sets of size k and sets of size 1. I still want to understand how this random walk works. If you look at properties of this random walk, you can pretty much derive everything you want to know, including mixing time, from just looking at the even steps of this random walk. So if you look at odd steps, you're on the top. If you look at the even steps, you're at the bottom. So if you just look at where you are at the even steps, that's like a random walk on just one set, right? And you can write down the transition probability of this random walk, and it's pretty easy to do. The probability of transitioning from some element I to some element j is just a conditional probability of j being inside your distribution, conditioned on I being inside your distribution. And this thing is, you have to actually divide this by 1 over k, because when you're at the top, there's a 1 over k chance of going to any element. Okay, so the properties of this random walk are entirely determined by properties of this by this matrix. So if I want to know that this random walk, whether this random walk mixes fast or not, I can just study eigenvalues of this matrix. Okay. In fact, I can, to make life simpler, I can subtract a trivial matrix from this random walk. If I subtract the stationary distribution from each row, I'm looking at the difference between two random walks, one of which is doing the bipartite walk, one of which is just jumping to the stationary distribution. And if I can bound the eigenvalues of this difference, then I can say something about the mixing time. Okay. Now this matrix in the middle is what I'm going to call the correlation matrix, non-standard notation, but easier for the rest of the talk. Okay. So the idea is we're going to show that whenever this matrix is spectrally bounded, your random walk, not just between k sets and 1 sets, but between k sets and any other level set is good. Okay. So this is what I'm going to show in the rest of the talk. That for any of the distributions I talked about, if you write down this matrix and drop the 1 over k, if you just look at the matrix in the middle without the 1 over k, the maximum eigenvalue of this matrix is just going to be bounded by a constant. And then I'm going to show that whenever this happens for your distribution and all conditionings of it, then your random walks between k sets and k minus 1 sets, or k sets and k minus 2 sets, or something like that, is going to mix in polynomial time. I think this is a good point to pause if there are any questions. OK. All right. Yeah.
So what are the structural properties of the distribution you're using, or just?
So I haven't said anything yet, right? So I'm just saying, OK, so this is a correlation matrix. You can write it for any distribution. I'm just saying whenever this correlation matrix, you can somehow bound its eigenvalues by a constant, then you get fast mixing. So I'm lying a little bit. So you have to bound this correlation matrix not just for your distribution, but for your distribution and all of its conditionings. But you know, the type of distributions that we are talking about are closed under conditionings. So it's, yeah. Yes?
It's easy to see for something simple, like maybe correlation decay, that this is like the lambda max is small?
So I'll get to that. Yeah, I'll get to that later in the talk. Yeah. Yeah. OK.
So the mixing time doesn't depend on n?
The mixing time does not depend on n. But each step, implementation of each step. So OK, so sorry. So this is the spectral gap of the random walk between k sets and k minus O of 1 sets. Of course, the mixing time depends on the probability of the point that you start with. And also, you know, you have to implement each step using an algorithm, and that's going to take time polynomial in n, right? So the probability of the starting point might also depend on n. So there might be some dependencies on n here, if you're turning this into an algorithm. So yeah, sorry, poly k mixing time. I should have said poly k relaxation time. But OK, no worries if you don't know. Yeah, don't worry about it if you don't know what that means. All right. So OK, so one quick aside. I'm not going to dwell too much on this, but I mentioned that there is this generalization of this notion of log-concavity, which is basically equivalent to having these correlation matrix, having bounds on the eigenvalues of these correlation matrices. And this is just the equivalence. I'm not going to prove it. I'm just going to state it. So Cynthia was working with polynomials that encode your distribution. So for each subset of size k, you have a value of your distribution, or the PDF of your distribution. You can multiply it by variables corresponding to the set. Sum this over all sets. You get a generating polynomial. And log-concavity of this polynomial was the theme of the previous talk. Fractional log-concavity is basically the theme of this talk. So fractional log-concavity means that if you replace the variables by some fractional power of them, so think of alpha as a parameter between 0 and 1. So if you look at this as a function in z1 through zn, if this is log-concave, then it means that the correlation matrix has bounded eigenvalues and vice versa. Okay? So you can forget this slide for the rest of the talk. That's all I'm going to say about it. Okay? All right. So why does this fractional log-concavity or bounds on the eigenvalues of the correlation matrix imply fast mixing? So this is basically a generalization of all of these ideas coming from the literature on high-dimensional expanders that Cynthia also pointed to. There is this phenomenon called local to global expansion. And I'm going to try to basically sketch this phenomenon as best as I can in just one picture. OK? So there are going to be things on this picture. No worry. So we have a distribution on subsets of size k. Okay? I'm going to generate this picture from my distribution by sampling a set of size k, permuting the elements of my set. And that permutation gives me a path in this tree from the top to the bottom, right? So for example, if I sample this 3 set, and then I order its elements like this one first, this one second, and this one third, I get a path in this tree. Okay? So that's how this tree is constructed. And you know, every node in this tree has a probability the probability is the probability associated to every node is the probability that it appears in this path. Okay. Now, if I have my random walk, so my random walk is what is it going to do? So let's say at some point in my random walk between subsets. So let's look at the random walk between sets of size k and sets of size k minus 1. Okay. So let's say at the beginning of the random walk, I am distributed according to this density with respect to my distribution. Okay. So there is a half times mu probability of being at this point. There's a 1.5 times mu probability of being at this point, and so on. Okay. So in my random walk, the first thing that I do is I drop one of the elements from my set of size k to go to a set of size k minus 1. And I do that uniformly at random, right? So I claim that after you do this, the probability of being at any of the k minus 1 sets is going to be is going to have density with respect to mu of this form, okay? Where these numbers are exactly just the averages of the numbers on the bottom. So for each node on the for each node of size k minus 1, I just took the average of the densities below it. I wrote that number next to it. Okay. So you can even continue this all the way up. So for example, if I'm looking at the random walk between sets of size k and sets of size k minus 2, the density in one step would be just the average of, I'm just taking averages of the nodes below a node, and those are the densities that you will encounter after taking one step of the random walk between size k sets and whatever size sets you want.
Why do you have a tree here?
There is there is really no need for a tree. I could have merged the similar nodes at every level, if that's your question.
I guess my question is like, why doesn't the bottom left node connect to the third node on the second layer?
Why does this one not connect to this one? Well, OK, so the thing is, this node actually has appeared multiple times in this picture, right?
Oh, I see.
So this node and this node are the same. So I could have connected them, but it doesn't really matter. Okay, all right. So now my claim is, look at the variance of these numbers that I've written on the bottom. My claim that the variance of the numbers at the next level are lower by a significant amount. Okay. So look at the fact that the variance of the number you write at the top, the numbers you write at the top, is just 0, right? There's just one number at the top. It's going to always be 1. It has no variance. Okay. The variance of the numbers that you write at the next level, it's actually going to be roughly 1 over k fraction of the variance of the numbers that you write at the bottom. That's the assumption that the random walk between k sets and the 1 sets mixes or has spectral bound O of 1 over k. Okay. So my goal is to show that when you go from the k sets to k minus 1 sets, the variance of the numbers that you see decreases by a significant amount. And in fact, I'm going to show that it decreases by roughly a 1 over k fraction. Okay. So how are you going to show that? You can just look at the variance of the numbers on the bottom and look at the difference of the variance to every level. Okay. So look at the difference of variance between k sets and k minus 1 sets, k minus 1 and k minus 2 sets, and so on. Right. So this difference at the top constitutes a 1 over k fraction of the whole thing. I claim that between level 1 and level 2, the difference between variances constitutes a 1 over k minus 1 fraction of the remaining variance. Okay. So how do I get that fact? I just look at the conditionings of my distributions. So these are subtrees rooted at nodes of level 1. And I use, again, the fact that for these conditioned distributions, I have a bound on the correlation matrix. So then the difference between the variance of these and the number here is going to be 1 over k minus 1 fraction of the numbers that you see on the bottom. Right? So in each level, when I go down, here I'm just consuming 1 over k fraction of the total variance. Here I'm just looking at 1 over k minus 1 fraction of the remaining variance, and so on. Right? So if you plug all of these numbers in, the variance that remains when you get to the last level is going to be roughly 1 over k. Okay? So this is a very high-level sketch. I'm happy to talk about it more if you want. But this is why when you have this correlation matrix bounds, you get fast mixing. Okay? So at the end of the day, this shows that when you go from k sets to k minus 1 sets, your variance decreases by a 1 over k fraction. But when you go back from k minus 1 sets to k sets, your variance can never go up. This is a fundamental inequality called the data processing inequality. So each step of the random walk between k sets and k minus 1 sets reduces the variance by roughly 1 over k fraction. Okay? All right. OK, so any questions about this? All right. So in the remaining time, I want to show you why we have these bounds on the spectrum of the correlation matrix for the models that I described. Okay. So the first example, this is just a warm-up, is when you have negative correlations like spanning trees. Okay. So here you can bound the L1 norm of each row of the correlation matrix. Okay. So if you look at a particular row corresponding to the edge E, you're just summing over all edges f, the conditional probability of f given E, minus the probability of, sorry, that should have been an f. This is a mistake. That should have been an f. Okay. Now, when you have negative correlation, what happens is that all of the terms in this absolute values have the same sign except for one of them. When E is equal to f, this is like 1 minus the probability of E. But for the rest, this is going to be a negative number. Right? Now the other thing I know is that if I drop the absolute values, the sum is 0. Right? Because the sum of the first probabilities is just going to be the number of edges in a spanning tree, which is constant. It's like n minus 1. The second term is also going to sum up to n minus 1. Right? So I have a bunch of numbers that sum up to 0. Except for one of them, all of them have the same sign. So when I take the sum of the absolute values, I'm going to get the magnitude of the sum of the absolute values is going to be the term that has the opposite sign. And that term is just something bounded between 0 and 1. Right? So the L1 norm of each row of this matrix is bounded by 1. That implies that the maximum eigenvalue is also bounded by order 1. Okay? All right. So let's go. So Cynthia talked about this. So let me just skip this. So when you have matroids or log-concave polynomials, you more directly get a bound on the eigenvalues of this matrix. But yeah, let me skip this. OK, so going to the hardcore model, back to your question. So it's not as simple as you might think, but the intuition is correct. So in the hardcore model, just as a reminder, this is a distribution on independent sets of a graph. So people have known for a long time that there is this decay of correlation phenomenon that happens when your parameter lambda is in some range. Okay, so there is this exact range. So for graphs of degree bounded by delta, there is this exact range. And if your lambda is below this number, you have decay of correlation. Above this, you don't have decay of correlation. And one of the amazing results in computer science is that this threshold of lambda, which corresponds to a physical phase transition, also corresponds to a computational complexity transition. So Alan Sly showed that if lambda is above this threshold, basically it's hard to sample from this distribution. And this is complemented by Weitz's result that shows that for lambda below this threshold, you can sample. But his sampling algorithm, Weitz's sampling algorithm, is not of the random walk type that I was talking about. So roughly speaking, the Weitz's algorithm basically corresponds to this. So for a vertex, Weitz would just look at a neighborhood of roughly this distance of that vertex, and because correlations are decaying with respect to the distances in the graph, basically what happens outside of this neighborhood of a vertex doesn't really affect the probability of this vertex being inside your set or not that much. Okay? So based on just local computations in this neighborhood, he would be able to compute the marginal of a vertex. And from computing the marginals, you can produce samples, right? So one of the caveats of this method that Weitz was using was that you have to look at roughly a neighborhood of size log n. Okay? And computation in a neighborhood of size log n basically takes time delta to the log n time, because you have max degree delta. Neighborhood of log n can have at most delta to the log n many vertices, right? So you get running times of this form where you can swap the order of n and delta, but the exponent basically does not depend on delta. Is a function of delta. Okay. Now it's been conjectured for a long time that simple Glover dynamics for this model in the threshold where you have decay of correlation should actually mix in time that doesn't depend on delta in the exponent of n. Okay, and this is what we can show now. So previously it was known that for a smaller threshold, roughly 2 over delta instead of e over delta, Glover dynamics mixes in truly polynomial time. But now using bounds on the correlation matrix, we can show that the Glover dynamics in the entire regime below e over delta minus 2 mixes in time n to n to some parameter that doesn't depend on delta. Okay. And I'm just going to say the intuition. When you have decay of correlations, roughly what that says is that if you look at 2 vertices u and v in your graph, the conditional probability of u given v differs from the unconditional probability as an inverse exponential in the distance between u and v. Okay, so that's what roughly decay of correlation means. And a first attempt would be to just use this to bound L1 norm of columns of this correlation matrix. So columns of this correlation matrix would be you fix the vertex u, you vary the vertex v, and look at how much it affects the conditional probability of u. Okay. So naively, this actually doesn't work. Naively, this doesn't work, and the reason is that the vertices at distance d, there are delta to the d many of them, but you only get e to the minus d decay of correlations. But using the same proof technique that was used to show decay of correlations, we are able to bound this sum and show that it's always bounded by O of 1. Okay. So the idea is decay of correlations, but it's not a direct implication.
So I guess if you had Debruchin, they would get it immediately. You can just
Yes. Yeah. Okay. All right. So now let me just go to the monomer distribution, which is the last example. So in the case of monomers, so as a reminder, the monomer distribution is on subsets of vertices of a graph, where the probability of a subset is proportional to the weight of matchings in the complement of that subset, right? Or equivalently, you can think of it as sampling a matching and then projecting onto the complement of the matching. Right? So this model doesn't have decay of correlations. It doesn't have negative correlations, but we're still going to be saying something about it. We are going to, similar to the negative correlation regime, show that the L1 norm of rows of this correlation matrix are bounded. Okay? But this is different from the negative correlation regime because I can't just drop the absolute values. Things have different signs here. Okay? But the strategy is so before actually I go into the proof, so this random walk between monomers of a graph, it's actually tricky to implement computationally because this weight given a set S, computing this weight corresponds to computing the weight of perfect matchings in the complement, which is still an unresolved problem. But for planar graphs, for example, you can compute this weight exactly. And this gives you an algorithm to sample from the monomer dimer systems in planar graphs. Okay? So even though computing or sampling perfect matchings in planar graphs is easy. Sampling from this distribution, the monomer-dimer distribution, is hard. It was shown by Jerome. So this is still a non-trivial result. So now let me show you how to bound the L1 norm of the rows of this correlation matrix for the monomer distribution. So we want to bound a sum of absolute values. So if somebody tells me where these absolute values have a positive sign and where they have a negative sign, I can just negate the corresponding terms and look at just the sum without absolute values, right? So let's say T is exactly the set of terms where, sorry, this should have been S. Yeah, this is a mistake. This should have been S. But T is the set of terms where this absolute value has positive sign. Okay? T is going to be some subset, and I don't really care what subset it is. Okay? Now, define a random variable x, which is you sample a set S from your monomer distribution, and you look at T intersection S minus T complement intersection S. So for the positive terms, I'm getting a +1 from this. For the negative terms, I'm getting a -1. So if I look at the expectation of this x, it exactly gives me this sum of absolute values. Okay. So the expected value of x would give me the sum of the first terms correctly signed. And the expected value of x would give me the sum of the second terms correctly signed. And the expected value of x, given that u is in S, gives me the sum of the first terms correctly signed. Okay? So at the end of the day, what I have to show is some sort of a smoothness property. I have to show that when I condition on vertex u being inside my monomer set, the expectation of x doesn't change by much. If I'm able to show that it changes by at most a constant, then that bounds the L1 norm of this row. Okay. Now, fortunately, we know some things about the monomer-dimer distribution in terms of polynomials, and that allows us to analyze what this distribution of this set X looks like. Okay. So first of all, this set X, if you work the parities, it's going to be always its support is always going to be either odd integers or even integers, depending on the parity of the number of vertices in your graph. But here is the amazing fact. If you divide it by 2, now it's going to be either on the set of integers or integers shifted by a half. It's going to be distributed according to a sum of independent Bernoullis plus maybe a constant shift. Okay. And I don't think I have time to give you the full proof of this, but let me just give you a sketch of where this is coming from. So if you have a univariate distribution, if you have a random variable taking on, let's say, integer values, and if you want to know whether it's distributed as a sum of Bernoullis, there is a correspondence in the polynomial language, in the polynomial world, which tells you whether this is true or not. And this correspondence is to the roots of the generating polynomial of this distribution. Okay? So you have this univariate distribution. What you do is you put the values of the distribution as coefficients of a univariate polynomial. And you just look at where the roots of this polynomial are. If none of the roots are complex, this distribution is a sum of Bernoullis and vice versa. Okay? So yeah. The rough proof is that whenever you have a factorization into product of linear real polynomials, you have the Bernoullis given by this factorization and vice versa. Okay? And the location of roots of this polynomial also tell you exactly where the biases of these Bernoulli random variables are and so on. Now, the thing we know about the monomer distribution is this result of Heilmann and Lieb from many, many years ago, that if you look at the generating polynomial of the monomer distribution, it has a special property that's usually called Hurwitz stability. So it says that when you plug in complex numbers with positive real parts, you never get a 0. Okay? So just by massaging this fact, you can get the fact that this distribution, the distribution of this variable x that we cared about, is just constant plus a bunch of independent Bernoullis. Okay, so it's an exercise. It's an involved one, but you can do it. Okay. All right. So now, so now we have the fact that the distribution of this x is of this form, but the distribution of x conditioned on u is also of this form. And in fact, these two distributions, the conditioned one and the unconditioned one, any mixture of them is also of this form. Because you can get the different mixtures by varying the weight of the vertex u that you are conditioning on. Okay. So we have two distributions that are basically sum of Bernoullis. And any mixture of them is also a sum of Bernoullis. I want to show you that their expectations should be off by at most a constant. Okay. So if you didn't understand any of that, here is a test problem that you can think about. So think of like two Gaussian distributions, right? They are log concave, they're unimodal, they're whatever property you want. And I can ask the question, are the mixtures of these two Gaussian distributions log concave or unimodal? Okay. So in this picture, all of the mixtures are going to be both log concave and unimodal. But if I start from Gaussians that are far apart, this is no longer the case. I get bimodal distribution somewhere, right? The same phenomenon happens when you're looking at sum of independent Bernoullis. Okay. If you only care about log concavity or unimodality, if the distributions are within some constant times the standard deviation of each other, you can have log concavity or unimodality always. But when the distributions are bounded away by more than a constant times the standard deviation, you can have bimodal distributions, right? Now, if you replace unimodality or log concavity with being a generalized binomial, I claim that you can have mixtures which are generalized binomials only when the expectations are off by at most a constant, not a constant times the standard deviation, but just an absolute constant. Okay, so this is the strange phenomenon that's happening here. And okay, so it's the last slide. This is a proof of this fact. I told you that that sum of independent Bernoullis corresponds to polynomials whose roots are real, right? So if I have two distributions whose mixtures are always sum of Bernoullis, I know that the mixtures of the corresponding polynomials are always real rooted. But there are well-known lemmas in the literature which tell you exactly for what types of polynomials this happens. This happens exactly when the polynomials have real roots which interlace each other. Okay? So there should be, so before the second orange root, there should be a first green root. And before the second green root, there should be a first orange root, and so on. Okay? So in particular, if you order the roots of the polynomials, before the ith root of each polynomial, there should be the I minus first root of the other polynomial, and so on. Right? So that also tells you that the biases of the Bernoullis also interlace each other. Okay? Because biases corresponded to the roots exactly. So if you order the biases of the Bernoullis between the two distributions mu and nu, these biases interlace each other. So the difference between the expectations of these two distributions, which is just the difference between the sum of biases of one and the sum of biases of the other, this can at most be 1. This difference is a signed sum of intervals over the that are contained between the 0, 1 interval. So the signed sum of their lengths can be at most 1. Okay. So yeah, so this just finishes the proof. All right, so let me conclude. So we started with just looking at matroids, and there having spectral negative dependence was very natural, corresponded to log-concave polynomials. But I showed you that spectral bounds on this correlation matrix can be proved for other models, like the hardcore model or the monomers distribution. So there are some natural questions here. One of them is, do you have to go through this machinery of log-concave polynomials to get the first result? Okay. So when we had negative correlation, we were able to bound the L1 norm of rows So for example, for the spanning tree, for random spanning trees, we were able to bound the L1 norm of rows of the correlation matrix. I don't know of any matroid where this L1 norm is unbounded, or any family of matroids where this L1 norm is unbounded. So it's a natural question. Do we have to use this log-concave polynomial machinery, or can we actually prove it using simpler means? Okay. So another obvious question is, are there other distributions that are natural and give you fractionally log-concave polynomials or equivalently bounds on the correlation matrix? So a conjecture is, if you look at subsets of size k as a 0, 1 polytope, so form their indicator vector and look at the convex hull, the conjecture is that if all of the edges of this convex hull have bounded length, then you should have fractional log-concavity. So this is in agreement with some old conjectures of Mihai and Vazirani. You can talk to me more about it if you want. Thank you.